We have previously determined the formula for the fatigue damage, and in particular we found that the damage, D, which can be evaluated as the expected value of a random variable related to damage, D with a tilde, this is equal to the expected value of the positive number of peaks per unit time, NP plus, multiplied by the duration of the signal T, divided by the constant C appearing in the high cycle fatigue formula. And then we have an integral from 0 to infinity of sigma to the power b. And then here we have the distribution of the peaks, fp, of sigma d sigma, which we can also write by using the linearity between sigma and displacements. So this is equal to E of np plus times t, and then here we have k to the power b divided by c, integral from 0 to infinity z to the power b, fp of z dz. Now, if we have a narrow-banded system, we know that the expected value of the positive number of peaks per unit time is approximately equal to the mid-frequency of the narrow band of the system. So let's call it Fn. And if we assume that the system is excited by a Gaussian signal, so that's the input to the system, then the response will also be Gaussian. This is quite intuitive. Since relative displacements are defined by the difference between the output and the input, x minus y, then z will also be Gaussian. Because when we have a linear combination of Gaussian variables, of course, we get another Gaussian variable. In this case, I should not use the word variable because we have a process, but it's a random variable which depends on time. We can call it that, and therefore that's a random process. Then this distribution here, the distribution of the peaks, is a Rayleigh distribution because we are talking about Gaussian processes. And therefore we can write the damage by using the formula for the Rayleigh distribution. So we have Fn t k to the power b divided by c, and then we have an integral from 0 to infinity z to the power b, and then here we have z divided by sigma z, which will be a function of f of n squared. So this is the standard deviation of the relative displacement z, and this standard deviation will depend on the natural frequency of the system, and we'll try to dig a little bit deeper in a few minutes. And then here I have e to the minus z squared divided by 2 sigma z of fn squared dz. Now let's rewrite this integral by making a substitution. We will make the substitution x equal to z squared divided by 2 sigma z squared, and of course dx will be equal to z dz divided by sigma z squared, and z to the power b is equal to x times 2 sigma z squared to the power b over 2 is equal to x to the power b over 2. And then here we can rewrite square root of 2 sigma z to the power b. So I have simply used the fact that we have this formula, and then you can obtain also that. And we can substitute. So pay attention also to the fact that the damage will be a function of the nature of frequency. So this is called the fatigue damage spectrum. It's quite important, or abbreviated as FDS, fatigue damage spectrum. It's a spectrum because for each different natural frequency, we might associate a different damage value. So the damage will depend on the frequency of the system. And if we model our material, in general, our system, our complicated material that we want to test in our lab. So we have some samples made of some material, and we want to test the material by means, for example, of a vibratory table. which is also called a shaker. So we input some kind of vibratory motion to the shaker, and the shaker will subject the material to some vibration, and therefore that will cause stresses. And depending upon the natural frequencies which are present in the material, we might cause different damages at different frequencies. That's the main idea. So it's as if we are modeling our system with different single degree of freedom systems in parallel that can be independently excited. But anyway, so the formula that we have after the substitution is the following. We have Fn t k to the power b divided by c, and then we have an integral from 0 to infinity dx. Let me put dx here. 2 sigma z squared x to the power b over 2 e to the minus x dx. And we can rewrite this as Fn t k to the power b divided by c 2 sigma z squared. So remember that sigma z is a function of Fn. So let me put it here. And then we have b over 2. And then we have the gamma function of b over 2 plus 1, where the gamma function of alpha is equal to integral from 0 to infinity x to the power alpha minus 1 e to the minus x dx. So this is the formula that we have for the damage. And this is the formula for the gamma function, which is well known. Now, sigma z, this sigma z can be related to the power spectral density of the input signal and also the frequency and damping of the system. So now we want to find the relation between sigma z and the power spectral density of the input signal. The input signal is called y. So the output is x, the input is y, and we can find the relation between sigma z and the power spectral density of the function y, and therefore also relation between the damage, the spectral, in this case the damage spectrum or the fatigue damage spectrum, and the power spectral density of the signal, which is very, very important and also used when dealing with vibratory tests related to fatigue. And I did a PhD dissertation on that, so there is much more to it than meets the eye. But I want to focus on the most important things, the foundations of this kind of theory, without wasting time on the details. Now, for a single degree of freedom system, we can write a relation, a differential equation, an ordinary differential equation between the input and the output. And in particular, the second derivative of the output. So instead of writing y, I should write x. This is the output. X double prime of t plus 2 omega n, which is the natural angular frequency. So this is equal to 2 pi fn times the damping coefficient zeta times x prime of t plus omega n squared x of t. And this is equal to the input multiplied by an appropriate variable which helps our units. So we have omega n squared times y of t. So this is one way to write the differential equation of a single degree of freedom system. So we can always write them in this form. Now, if we are interested in the relationship between the Fourier transform x of omega and y of omega, so we want to find the transfer function between these two variables. The transfer function will be f of omega, for example. Let's call it f of omega. So x of omega will be f of omega times y of omega. And if we find this function, we will also be able to find the power spectral density and the relation between the power spectral density of the input and the output, because we know that the power spectral density will be related to the square of the variable, so of x in this case, or the square of y. So the square of y will be related to the power spectral density of the input. And in general, we have random processes. So this signal here should have a tilde to denote the fact that we consider a random process, and also the Fourier transforms, but there will be no randomness in the system, so f of omega will not have a tilde. So how do we find the function f of omega? How do we find this relationship? Well, we have to deal with Fourier transforms here, so we have to transform the ODE, and we have to apply basically the Fourier transform, and therefore I'm using the variable omega here, so x double prime will become minus omega squared, and it will multiply x of omega, but I'm going to factor out x of omega here. And then I have plus 2 omega ni zeta omega. And then I have plus omega n squared. And this will be equal to y tilde of omega times omega n squared. Now, usually when we deal with vibrations, our signals are indeed accelerations. In the formula for the damage, we have displacements. So we need to convert the accelerations into displacements. We know in general that z of omega, the acceleration, so let's put two dots here, will be equal to x of omega minus y of omega. And if we want the displacements, we need to find z of omega. And how do we find the relationship between z double dot of omega and z of omega? It's quite a simple relationship because z double dot of omega is simply equal to minus omega squared z of omega. And now, since this is equal to x of omega minus y of omega, from here we can find x of omega equal to minus omega squared z of omega plus y of omega. And we can substitute it in here. So when we do that, we get minus omega squared. Then here we have minus omega squared plus 2 omega ni zeta times omega. And then we have plus omega n squared z tilde omega. This is equal to omega n squared plus omega squared minus omega n squared. So this will cancel. And then we have minus 2 zeta omega n omega I y tilde omega. And from here we find the function f of omega, right? So we get, so if we divide everything by this, we have z of omega equal to the transfer function multiplied by y of omega. And we can also square z of omega and take the magnitude squared of z of omega. And this will be equal to omega to the power 4 plus 2 zeta omega n omega squared divided by omega to the power 4 omega squared minus omega n squared plus 2 zeta omega n omega squared. And this multiplies mode of y tilde omega squared. And now we can take the expected value also of this and also of the right hand side. So we will have an expected value here of this. But what is the expected value of y tilde omega? Well, that is simply the power spectral density, right? The bilateral power spectral density, Sy of omega. And on the left, here we have Sz of omega. So this is the relationship between the power spectral densities. And this relation will also hold if we consider the one-sided power spectral density. So here we can put g z of omega, and here we can put gy of omega. And we can also define, for example, the variable h as omega divided by omega n. So this will be dimensionless because we divide the frequency omega by the natural frequency of the system. And we can rewrite the relation by integrating on the left here this function over omega. And if we integrate that over omega from 0 to infinity, we get the variance sigma z squared. This will be a function of fn squared. It's an integral from 0 to infinity of h to the second power. Here you have omega to the power 4, but you can see that you can factor omega squared from here, and you can cancel omega squared also from here. So you can simplify this expression a little bit. So here you have omega squared, here you have omega squared, and here you can remove omega. So when you rewrite everything in terms of h, you have h squared plus 2 zeta squared, then you divide by h squared, you have h squared minus 1 squared plus 2 zeta h squared. And then here you have dh, and you also have to divide by omega n cubed, if you do the simple calculation, which is 2 pi fn cubed if you want, like this. And you also have gy, which will be a function of h in this case. It is written with respect to h, right? So you have gy of omega, but omega will be itself a function of h from here, right? Also, we have to be a little careful here because there is another factor of 1 over 2 pi, and let me try to explain why this factor appears. Because sigma z of fn squared is defined as the integral from 0 to infinity of gz of the frequency f and integrate over f. So if you want to define this integral with respect to omega, so you have gz of omega d omega, and df is actually equal to d omega over 2 pi. So it really depends on how you define this function, because you can define also the function like this, but at this point, I mean, this is a different function with respect to this one. So you might call this g hat. I don't know, it's a different function because it depends on omega here. But the difference between them is simply a constant, and this constant is 2 pi, right? So basically, if you want to keep the same function here and here, then you have this factor of 2 pi. So if you define the function like this, and in order to be consistent, that's what we did on previous occasions. So you have another factor of 1 over 2 pi to consider here. Because in here we are integrating over the omega, over omega. So we defined everything in terms of omega, and therefore it's appropriate to keep into consideration this factor, but it's not really the key here. It's just to be careful and show you these subtleties. And this is what we get. So this is the formula which gives us the relation between the input power spectral density and the variance of the relative displacement, which appears in the formula for the damage. And this formula is something that you can also discretize. So speaking of numerical computations, and because this is useful when you work with a computer, when you're working on a computer, you need to discretize these formulas. So sigma z depends on fn, the nature of frequencies. And if you have a spectrum, you have to discretize the spectrum with respect to fn. At the same time, the power spectral density depends on the angular frequency omega. So in this case, it's h. So we can speak of the variable h and you can discretize h, but h is different from fn. And therefore here what you will have a matrix which multiplies the vector gy, which depends on h. So the matrix contains the index related to h, if you discretize it, and also the index related to fn, because it also appears in the formula. So there you have you can rewrite everything in terms of linear algebra notation. So sigma z of fn squared will be some matrix a n k. So let's use this index n as an index which discretizes this frequency, which is not really appropriate because n here stands for natural. But now let's think of n as an index that can take the values 1, 2, 3, dot, 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 up to the final number of the spectrum. I don't know, it can be whatever number. And k instead discretizes the power spectral density. So it will be gy sub k, like this. And we have a matrix. So if we invert this matrix, we can, for example, find the power spectral density by knowing the standard deviation of the relative displacement. And the standard deviation of the relative displacement is related to the damage. So we can also find the relation between gy and the damage. In particular, gy sub k will be the inverse of a and k, so we can rewrite it as a inverse kn, and this will multiply this, and we can rewrite it by using the formula for the damage, which is 1/2 d of fn times c divided by fn t k to the power b gamma function of b over 2 plus 1 to the power 2 over b. And this is actually very important. I've used it very often in my PhD dissertation and while running experiments, because this helps synthesize signals starting from a damaged spectrum. In particular, in real applications, when you have a signal that you measure, you can measure a signal with accelerometers, and this might be a recording of an acceleration of a certain object. This object might be a mechanical object or even electronic component. It really depends on the application. It is very general what we are talking about here. And for example, this kind of signal will lead the component to failure within, I don't know, several years even. This might be a very long signal. Of course, there is no possibility of recording signals that last this much. It is not possible. But in general, the signals that lead components to failure have a duration of the order of thousands of hours, or even more than that. So, in principle, these signals might be very long, and you can think of signals that lead components to failure. The signals, so instead of considering the entire lifetime of the component, we can consider only a small portion which is representative of the signal itself. So we are assuming that the statistical characteristics of the signal can be visualized very well, even if we take a smaller portion of our signal. And from the signal, we can calculate the fatigue damage spectrum, or the FDS, over some kind of a spectrum embodied by the frequency Fn. This fatigue damage spectrum can be calculated by using standard techniques. I have mentioned one of these techniques in one of the previous videos, and the important technique is the rainflow counting. This technique allows to count the cycles which are present in the relative displacement signal, and the relative displacement can be calculated from the input signal by knowing the characteristics of the linear system, so the single degree of freedom system, as we saw earlier. And there are techniques that allow to do that. So I don't want to focus too much on that. But anyway, from the fatigue damage spectrum, it is possible to calculate a power spectral density. And you can see that the power spectral density also depends on the duration of the signal that we want to impose. So in this case, we can impose a certain duration, for example, a shorter duration, and at the same time, we can synthesize a PSD which is related to this damage. And if we synthesize a signal from the PSD, which is a very standard also, there are standard techniques that help do that. And in particular, the signal that you will create will be a Gaussian signal because of all the assumptions that we have made. So the signal that we will synthesize from here will have a certain duration that we can impose, and the signal will be Gaussian. So in general, Gaussian signals have a very well-defined shape. Their shape is very easily recognizable. Now, I don't want to speak about that. But for example, they cannot contain portions of signal where, for example, we have very high peaks and then the signal will behave like this, and then we have very high peaks and the signal will behave like this. No, it will not be like this. It is not possible for a Gaussian signal to behave like this. This might be also very non-stationary signals. And I've also discussed these kind of signals in my PhD dissertation, but this is not the right place to discuss this. I just want to give you an outline of the theory. But this is actually very important because if we synthesize a signal, even if it is Gaussian, this signal preserves the damage which was, for example, contained in this signal here, which was a different signal with a different distribution, but it might also have had a different duration. This was the duration of the signal, whereas here we have a different duration. But over this duration, the signal will exert the same damage onto the component, onto the samples, the specimens, whatever you want to call them, on the material. This technique is used to accelerate fatigue tests.